Today we're going to be doing lesson 10.2, which is the difference of two means using independent data sets. I'm going to read the definition or the first paragraph of the section. Many practical applications of statistics involve a comparison of two population means or two population proportions. In section 10.1 last week, we considered tests of differences of means for dependent samples. With dependent samples, we could pair the data and then consider the differences of the data measurements, D. In this section, we will turn our attention to inferences regarding the differences of means from independent samples. And the definition of independent samples is two samples are independent if the selection of sample data from one population is completely unrelated to the selection of sample data from the other population. So, to describe it differently, last week we did hypothesis tests about data sets where the sample size of data set 1 was equal to the sample size of data set 2, and the data points could be directly mapped to one another. So, meaning that the first data point of sample set 1 was equivalent or directly mapped to the first data point of sample set 2, and the second of 1 mapped to the second of 2, and so on. I'm getting all these numbers mixed up. But today we're doing an independent sample where the sample size of N1 does not equal the sample size of N2. So our first test could result in 10 data points. Then our second set could involve 12 data points. We're going to use an example like that later on. And then those data points do not directly map to another data point. The two samples are independent of one another. Independent. Yeah. And these are dependent. So this is what we're learning today, how to run a hypothesis test on sample sets that are dependent of one another. We're going to introduce some new things. So we're going to redefine our X bar for the difference of two means using independent data sets. X bar is now going to be the difference of the X bars of the two data sets. So we're going to have X1 bar minus X2 bar. Our mean, mu, is going to be the difference of the means of the two data sets, mu1 minus mu2. And our standard deviation, sigma, is going to be a little bit more complicated. It's going to be a function of the difference of the standard deviation and the sample size of one data set to the other. So what that means in equation form is that the standard deviation of the first data set squared divided by the sample size of the first data set plus the standard deviation of the second data set squared divided by the sample size of the second data set under the square root is going to equal our standard deviation. So this should extend all the way down. So these are our new equations. Now let's look at page 421 where we have the procedure. I have this in my book, but it just occurred to me that it's possible you do not have this in your book. I hope you do. It would be very helpful if you did. If not, then let me know. I suppose on my book, page 421, it shows me the exact procedure that we're going to use to solve these, or to run these tests. So like point one, well, first what we're testing is a difference in the means of the two data sets. We have to have a null hypothesis. So the null hypothesis for this type of test is always going to be H naught, that the difference of the two data sets is 0. There is no difference, which means the other alternate hypothesis is going to be, are they different? That could mean is mu1 greater than mu2? Is mu1 less than mu2? Are they just different at all? And we will determine that based on what the problem statement asks of us. The main different thing, this test is going to be run in a very similar way to every other hypothesis test that we have run. The difference is we're going to calculate our test statistic differently, but it's not going to be too different because before, remember, the basic equation for the test statistic is x bar minus mu divided by sigma. Well, we have redefined these above, which means we can plug in our new definitions to make the test statistic equation for independent data sets, the difference of independent data sets. So what that's going to look like is x1 bar minus x2 bar quantity minus the quantity of mu1 minus mu2. And that's going to be divided by this big boy right here, the square root of sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. Now, since we are testing that the difference of mu1 and mu2 is 0, we can just take this out and simplify the test statistic equation to be x1 minus x2 bar, of course, divided by this, and I guess I don't want to write it out again. You guys get the picture. We can just do this, right? So this is our equation. X1 bar minus x2 bar divided by this big mess down here. It's going to take us a little bit longer to calculate our test statistic, but once we do, and it's not actually that hard of a calculation, we're set. We are going to solve, we're going to run the test as normal, as we always have, where we're going to find a p-value based on z, and we're going to compare that p-value to the level of significance, and then come to a conclusion. Now, we are also going to do, let's pull that to the side, we're also going to learn how to do confidence intervals with this as well. So remember, a confidence interval for the mean looked kind of like x bar minus some error. So mu greater than x bar minus some error, and mu less than x bar, the same x bar, plus some of the same error. So since we usually start with x bar, all we had to do was solve for e, and then we have the confidence interval, and we typically wrote it in this format, this x bar minus e comma x bar plus e ordered pair style format. And what this means is, to a certain level of confidence, mu falls within this range. Like, we're 90% sure mu is within these boundaries, or we're 95% sure. Well, we're going to do that here. Our new our new margin of error, E, is going to equal the critical Z value, ZC. Remember, we take our level of confidence, we find the value for this in table 3B in the appendix. That's how we find the critical Z value. And we're going to multiply that by the square root of our standard deviation, which is this equation, which is annoying to write down, especially with a mouse. Dang it. With this equation here. And we can do that. We've already calculated this actually over here. So I might even recommend that once you calculate your sigma over here for the Z score, you make a note of it, because you're going to use it in a couple minutes. So now that we've given the equations and the building blocks, let's do example 4 in the book, and let's see all this work. So I'm gonna keep this over here. I'm probably not gonna have enough room, but let's try it. So the prompt is: a consumer group is testing camp stoves. To test the heating capacity of a stove, it measures the time required to bring 2 quarts of water from 50 degrees Fahrenheit to boiling. 2 competing models are under consideration. 10 stoves of the first model and 12 stoves of the second model are selected at random and tested. The following results are obtained. So let's go ahead and write down what we have. I'm going to box that off. We have that our first sample size consists of 10 stoves. Our second sample size consists of 12 stoves. Independent data sets. There is nothing tying these two data sets together. And then we also learn that model 1 the mean time it took to bring the water to a boil was 11.4 minutes. That's a long time. And the second model had a mean time of 9.9 minutes. Assume that the time required, okay, it doesn't matter. So now we're asking, is there, I missed something. We have a standard deviation of the first one of 2.5 minutes. I thought I was missing something. And then the standard deviation for the second is going to be 3 minutes flat. Okay. Now we have all of the values that we need to find our z-score and our margin of error, which is great. Now we just need to figure out, what are we testing? So the hypothesis test is there any difference at all between the performances of the two models? Use 5% level of significance. That means our alpha value, our level of significance, is going to be 0.05. We are going to state the null hypothesis. The null is always going to be that the difference of the two means is 0. And now we will write our alternate hypothesis, which does change, and that is going to be that the difference of the two means is not 0. Basically stating, are they different at all? Are they different to a certain degree that matters, basically? So Now we can run the test. We can compute our test statistic. So that equation is right here. Let's calculate z. Z is going to equal x1 bar, 11.4 minutes, minus x2 bar, which is 9.9 minutes. That's going to be divided by the square root of sigma 1 squared, which is going to be 2.5 squared over 10, because that is our the sample size of the first data set. And we're going to add to that 3 squared, because that is the standard deviation of the second data set, divided by 12. So let's go ahead and make a note that our combined standard deviation, if I knew where my calculator was, there it is. So let's see, 2.5 squared divided by 10, that's being added to 3 squared divided by 12. We take the square root of that, and that gives us 1.173. I'm going to check that with the book. The book doesn't give us an intermediate value of sigma, but we're going to write that off to the side. The difference of 11.4 and 9.9 is 1.5. So that means we're going to take 1.5 and divide it by this number right here to get a z-score, a test statistic of 1.28. That does match the number in the book, so we're in business. Now we need to find a p-value of this test statistic. So we're finding the probability of z less than 1.8 with this statistic right here. But remember, this is a two-tailed test. So what we actually are interested in is 2 multiplied by 1 minus the probability that z is less than 1.28. So we will go to our table. In the appendix, table 3A, and for a z-score of 1.28, we get that the probability that z is less than 1.28 is 0.8997. So 1 minus that is 0.1003 times 2 is 0.2006. So this right here came out to be 0.8997. We subtracted that from 1 because we're not interested, if we were to look at the curve, that test statistic. Let's draw a nicer curve. I am so bad at drawing these. Our test statistic was finding everything on this side, right? But we're not interested in that side. What we're interested in is this over here and this over here. So our test statistic that was finding all of this, we take 1 minus this to get the little part over here, and we multiply it by 2 to get the little part over here. And that is equivalent to 0.2006. So now we are going to compare our p-value right here to the level of significance alpha. Alpha is 0.05. our p-value is much greater than our alpha value. And that means we do not have sufficient evidence to reject H naught. So we do not I'm just going to write it this way, that H naught is good. We do not reject H naught. And to interpret that, we would say that at a 5% level of significance, the sample data does not indicate any difference in the population mean times for boiling water for the two stove models. That means this hypothesis is true. There is not a significant enough difference in the two stoves to warrant producing one over the other. So now we want to find a confidence interval for mu. And well, let's just do it first, then I'll explain why it's important. I'm going to hide most of this. And now let's calculate. So over here we saw that we want to make an ordered pair of x bar minus e and x bar plus e. We've already calculated x bar. That was this quantity, right here. That was 11.4 minus 9.9, which is 1.5. So our new combined x bar, is 1.5. So now we just need to calculate the margin of error E to a 95% confidence. So we're going to go to our appendix, we're going to look at table 3b and look at the confidence interval critical values ZC, and we see that at a 95% confidence, our critical value is 1.96. So we're going to begin this margin of error equation with 1.96, and we're going to multiply it by our standard deviation that we calculated earlier, which we have put that off to the side. That is 1.173. So by going ahead and making a note over here, we saved ourselves having to write all that out again. Multiplying those together, we get 2.3, which means our confidence interval, which I'm going to write in ordered pair form, is 1.5 minus 2.3, comma 1.5 plus 2.3. So when we do this math, that's going to give us a negative 0.8 minutes. And a positive 3.8 minutes. So the way we would say this is we are 95% confident that the difference of our means lies within this range, negative 0.8 minutes and positive 3.8 minutes. I'm going to read something from the book. Notice that the confidence interval contains both negative and positive values. At the 95% confidence level, we cannot conclude that mu1 is either less than or greater than mu2. This result is consistent with the conclusion of the hypothesis test, that is, at the 5% level, the evidence is not sufficient to conclude that there is a difference in the average times for boiling 2 quarts of water between the two types of stoves. Now, there is on page 423 a little procedure box that tells us how to interpret confidence intervals for differences. So, at a certain level of confidence, they label it as C percentile. What that means is like that could stand in for 90% confident or 95% confident, whatever. This is just that confidence level in variable form. The three ways you can interpret it is the C% confidence interval contains only negative values. In that case, we conclude that mu1 minus mu2 is less than 0. And we are therefore C% confident that mu1 is less than mu2. And that's just taking this mu2 and adding it to both sides of the equation to result in this conclusion here. So if our alternate hypothesis was is mu1 less than mu2, we could conclude yes, it is, if our confidence interval contains only negative values. If our confidence interval contained only positive values, that means that the difference of mu1 minus mu2 was exclusively positive. That means that mu1 is always greater, the mean of 1 is always greater than the mean of 2. The third point is the C% confidence interval contains both positive and negative values, just like we had in that example. In this case, we cannot, at the C% confidence level, conclude that either mu1 or mu2 is larger. However, if we reduce the confidence level C to a smaller value, then the confidence interval in general will be shorter. Remember that the less confident we are, so like if we were to change a 90% confidence to a 70% confidence, our range of like x bar minus e comma x bar plus e is going to get smaller. So since in the last problem we had a confidence interval of negative 0.8 and positive 3.8, if we had reduced our confidence level enough, we might have gotten to a point where our values were only positive. And so instead of not having a conclusion, instead of saying that there is no difference between the means, we could now say that this case is true. The mean time of the first data set is consistently larger than, greater than the mean time of the second data set. Guided exercise 4 goes into more detail on how to interpret a confidence interval for the differences of means. So what if we want to run a hypothesis test on the difference of means? However, the standard deviations of the two data sets are unknown. So sigma 1 and sigma 2, we do not know them. We have a tool that we've learned before called the student's t-distribution that we can use, where we're using sample standard deviations instead of population standard deviations. The equations are almost the same. Basically, we're going to take the previous equations, and everywhere that we had a sigma, we're going to put an S in. And instead of using the Z statistic or the normal distribution test statistic, we're going to be using the student's t-distribution statistic. So the equations for that is going to be our test statistic t is going to equal x1 bar minus x2 bar. Now we'll subtract from that mu1 minus mu2, but we know that's going to be 0 anyway, so we're not going to write it. And that's going to be over our new S sample standard deviation of S1 squared over N1 plus S2 squared over N2. Now, this approximation is not exactly a student's t-distribution. There's some error in it, but there is something we can do to get a more conservative estimate, restrict the test, and so glaze over that inaccuracy so that, so remember how it's better to reject a true hypothesis than to fail to reject a false hypothesis. Using a more conservative method means it's more likely for us to reject a true hypothesis and less likely for us to fail to reject a false hypothesis. So what we're going to do is when we have the two different sample sizes N1 and N2, where before we found degree of freedom equal to N minus 1, we're going to take the smaller, so the minimum of N1 and N2, and our degree freedom is going to be the minimum, the smallest sample size between N1 and N2 minus 1. We're also going to learn how to make confidence intervals with the student's t-distribution, and it's going to be the same method. However, this time our equation for E is going to equal our t, test statistic, times this right here, which is going to be S1 squared over N1 plus S2 squared over N2. Now, we are going to do example 5 and practice using t-distribution instead of standard normal distribution. So I'm not going to read the problem statement. I'm just going to pull out the important information so we can just run the numbers. X1 is going to be 21.8. X2 is equal to 18.9. We could go ahead and just, these are bars. We can go ahead and just find our X bar because we're really never going to use X1 apart from X2. Our X bar is going to be 2.9, which is just X1 minus X2. We're going to have our sample standard deviation for the first data set be 8.7. Sample standard deviation for the second data set be 7.2. Our sample size number 1 is 12, and our sample size number 2 is also 12. So typically we would take, to find the degrees of freedom, we would take the lesser of these two data sets. However, they're the same, so 12 minus 1 is 11. We have 11 degrees of freedom. So our test is, we're going to say that our null hypothesis is always mu1 and mu2 are equal. In other words, the difference of mu1 and mu2 is 0. So we want to run a test. We're going to use a 5% level of significance. So our alpha value is equal to 0.05. To test the claim that there is no difference in the mean time required for bodily absorption. That would have been explained in the problem statement, which we didn't read. So basically, we're testing, just like the last problem, a two-tailed test. Is there any difference at all? Okay. So first, we are going to calculate t. So our t value is going to be x1 minus x1 bar minus x2 bar, which we already know is 2.9. That's going to be divided by our s, which is going to be the square root of 8.7 squared divided by 12 plus 7.2 squared divided by 12. Now we want to go ahead and figure out what this is by itself, because it's going to be useful to us later when we do a confidence interval. So we're going to take 8.7 squared divided by 12 and add to that 7.2 squared divided by 12. The square root of that number is 3.26. So we're going to hold on to that. And then the answer of this, our t value is going to be 2.9 divided by that, and that is 0.8. It's 0.8896. That's probably going to be rounded into 0.890. And the book answer is different because this s is not equal to 7.2. There is a mistake in their book. So at first they give S2 as 7.2, but later on they use a value of 7.5. So we're going to rewrite that as 7.5, and we're going to have to run these numbers again. So the t value is not going to be 0.89, it's going to be 0.875. Also, our s value is going to change as well. And redoing that calculation, we're going to have 8.7 squared divided by 12, adding 7.5 squared divided by 12. The square root of that is 3.32. A little bit different. Okay. Now that we have a value for t, we can go to our table and we can find an interval that p-value is within. Remember that with the tables we can't find an exact value for p with t distribution. We could if we had a calculator, but we don't, so we're going to go down on the table. I did not pull a picture of it up this time, to 11 degrees of freedom. Then we're going to go over until we find the interval that contains the t value of 0.875. So that's going to be between 0.697 and 1.214, which means for a two-tail area, our p-value is going to lie between 0.25 and 0.5. So now that we have an estimate for the p-value, we can conclude the test. So at a minimum, our p-value is going to be 0.25. 0.25 is greater than our level of significance, 0.05. That means at a minimum, t is always greater than alpha. And when p, did I say t? When p is greater than alpha, we reject the null we fail to reject the null hypothesis. So the null hypothesis H naught is good. So to say that in words, the verbal interpretation would be at a 5% level of significance, there is insufficient evidence to conclude that there is a difference in mean times for the remedies to reach the specified level in the bloodstream. So now that we have concluded the test, we want to do a confidence interval, and that's going to be pretty quick because we already have a calculated S value. We just need to figure out what our T is. So since we want a 95% confidence interval to pair with our 0.05 level of significance, we are going to go back to the T table. We are going to find that at a confidence level of 0.95 and a degree of freedom of 11, our T value is going to equal 2.201. So we'll go back to our example and we'll calculate our margin of error. That's going to be equal to that T value of 2.201 multiplied by the S that we calculated, which was 3.32. So our margin of error is going to equal 7.3. So our confidence interval then is going to be x bar of 2.9 minus this e, and then x bar of 2.9 plus this e. So that's going to be 2.9 minus 7.3 and 2.9 plus 7.3, which is going to give us the interval of negative 4.4 and 10.2. And we can see that since we have positive and negative values, we cannot reject the null hypothesis. I had to recreate, I grabbed this online, so I had to recreate what your critical values for student T distribution looks like. But when we are finding the T statistic for a confidence interval, we will take our level of significance. We're going to have a little dash C and a bunch of values here. At a 95% level of significance, we're going to use the 0.95 value and go down that column. That is pretty much everything for this chapter. Example 6 goes into critical region method, but it's exactly the same to what you've already learned. You've already learned critical region method. This is just using it for this specific kind of test, and it's no different. So I'm not going to go over it again. Homework for this week is going to be in chapter 10.2, problems 2, 3, 5, 7, 9, 12, and 16. If you have any questions, please let me know. Otherwise, have a good week.